Well, this workbook has three problems under the category of at least probabilities. And I thought it might be easiest just to treat those with this picture in a picture format rather than go to the light board. The first problem says the probability that Luis will pass his statistics test is 0.49. Find the probability that he will fail his test. So this is purely a problem about finding complements, yeah? So you would look at this situation with this really simple Venn diagram, right? The outer rectangle is the sample space, the circle in the center are all the pass outcomes, all the ways that Luis could pass his test. And what we're told is that the area of that circle is 49% of the area of the sample space. The sample space contains all of the outcomes with regard to taking this test. All the pass outcomes are inside that circle. All the not pass outcomes are outside the circle, inside the square. So if there's 49% of the area inside the circle, there's got to be 51% of the area outside. So it's really just as simple as that. And that problem is there. The problem is there because this skill of finding complements is what you need in order to do at least probabilities. So the probability of pass plus the probability of fail has to be 1. You take a test and something has to happen. You got to pass or you got to fail. If it's 49% pass, it's got to be 51% or 0.51 to that probability that he might fail. So here's problem 2. Problem 2, a little bit more complex. It says DVDs are reported to have a defect rate of 0.5%. What's the probability of getting at least one defective disc in a lot of 50? So I think the way you have to think about this is you're at a factory making DVDs and they're making hundreds of thousands, if not millions of DVDs per day. You grab 50, okay? You pull 50 off. Now, is that with replacement or not replacement? Remember, that's going to be an important concern. And this is a situation where it's clearly not replacement. You pulled 50 out, right? Maybe you pulled out 1, then you pulled out 2, but you're not replacing and putting back. But the population is so big that the population with or without the 50 is essentially the same. So you really treat each one of these removals of a disc, if you do it one at a time, as an independent event. All right, so that's getting started. The next thing you note that if what you're interested in is the probability of getting at least one defective disc, that's a hard problem, right? Because at least one means 1, or it means 2, or it means 3, or 4. Notice I'm saying or every time, or 50. You have to find the probability of 1 plus the probability that 2 are bad, that the probability that 3 are bad, and you have to add those all. You have to add those all together. Tough problem, unless you approach it a different way. And the way you would approach it is through the complement. And here I'm using the apostrophe here to indicate the complement, because just as we saw in the previous two slides back, the probability of at least 1 plus the complement of the probability of at least 1. Well, that's 1, isn't it? So if I can find the probability of at least 1, the complement of at least 1, I can subtract that from 1 and find the probability of at least 1. And if that's easier to do, we've already seen that finding the probability of at least 1 head-on is got 50 separate calculations in it. If that's easier to do, let's do it in that manner. And so the issue becomes, like in problem 1, what does it mean to be the complement of at least 1? And the answer is, and this is often the answer, the complement to at least 1 is none. No defects within 50. Yeah? So instead of at least 1, the absolute opposite, if you will, the complement of that is no defects. And that we can calculate, right? We can calculate that, treating each one of these removals of a disc as an independent event. The probability that that disc that you've taken is not defective, if the probability is that 0.5 that it is defective, and the probability that it's not defective is 1 minus 0.5 or 0.995. Every time I pull one out, there's a 0.995 chance that it's good. So it's 0.995 times 0.995 times 0.995 50 times, or 0.995 to the 50th, which would then give you the probability of no defects within 50. That number, by the way, is 0.778. If I subtract 0.778 from 1, now I'm back to the probability of at least 1, and that's 0.222. And that's the answer. So that's a classic at least problem, right? The problem itself head on is awful difficult to do. Let's, instead of finding the probability of at least 1, let's find the complement of that. Oftentimes, not always, you'll see in the next the next problem, this is not the case, but generally the complement of at least 1 is none. If that's easy to calculate, do so. Subtract that value from 1, you're back to the probability of at least 1. Okay, and here's the last of these 3 problems. This says, each of 5 boys randomly choose a watch from 12 different styles. What's the probability that at least 2 boys choose the same style? So we're right back to where we've been before. At least 2 boys means 2 boys, or 3 boys, or 4 boys, and 5 boys. And oh, by the way, you know, the probability that 2 boys match, well, is it the first boy and the second boy, or the second boy and the third boy, or the first boy and the fifth? You know, you've got to take all of those considerations into account. It's, as before, a very complex problem head on. And so instead, let's take this strategy to attack these at least problems by using the complement. And again, what is the complement of at least 2? Generally, the answer would be, the complement of at least 2 would generally be 0 or 1. But in this case, and you'll see that many times coming up in this course, but in this case, each 5 boys randomly choose a watch from 12. What's the probability of at least 2 boys? It doesn't make any sense to calculate 1. One is nonsensical in this case. 2 boys can match, 3 boys can match, but 1 boy can't match, right? There's no way to do that. So what we're really doing is saying that the complement of at least 2 is not 0 and 1, it's just 0. So we're back to, can we calculate, how can it be that each of these boys picks a watch and none of them match? And here's the way you would do it. Let's just lay down 5 slots. Okay, and how many ways can that first boy pick a watch out of 12? Well, 12 ways. All right, so the second boy then needs to fill the second slot, and he has to do so with a watch that does not match. There's 11 of those. Yeah? And likewise, the third boy now has to fail to match. He's got 10 ways to do that. The fourth boy, 9 ways. The fifth boy, 8 ways. So there's 5 different events with 12, 11, 10, 9, 8 different ways. The fundamental counting theorem says the total number of ways that those 5 boys can pick 5 watches from 12 styles is 12 times 11 times 10 times 9 times 8, or 95,040. And yet the total number of ways in the sample space is 12 times 12 times 12 times 12 times 12, 12 to the 5th. If we divide those two, we get the probability of no matches, 0.3819. And if I subtract that from 1, I'm back to the probability of at least 2, and that's 0.618. All right, so those problems all go the same way. I think once you get into them, you'll find that each one sort of goes the same way. I've kind of shown you the broadest bandwidth I could on problems of that type. So work a couple of those, and I think you'll be feeling safe with them. All right, very good.